Hello, welcome everybody to Zach's presentation on common misconceptions on machine learning. Zach is an expert in data science and machine learning. He actually holds a PhD in machine learning. He has written 6 books for Technics Publications, our publishing company, in data science, machine learning, artificial intelligence, Julia, and you'll see pictures of his books on his slide. He also has created over 100 videos for us in the Safari platform over the years. So a real recognized expert in the fields of machine learning, data science, artificial intelligence. He also has a passion for new technologies and Internet of Things, cybersecurity, as well as literature, music, and videos. So welcome, Zach. Very, very happy to have you here with us.
Thank you, Steve. Thank you very much. And hello, everyone. And I'd like to welcome you to this talk about the most common misconceptions on machine learning. As Steve mentioned, I'm Zacharias Voulgaris, and I'm a data scientist. And for the past couple of months or so, I'm also the chief data science officer at this company called Sphere XR. And this company deals with remote learning and education in general using virtual reality and this kind of technology. And as Steve mentioned, these are the books that I have published so far in data science, mostly. And for those of you who might want a copy of this slides deck, you can use this QR code on the right. Machine learning is a pretty broad topic, and it's really hard to do it justice, even if I just focus on the misconceptions about machine learning. But I'll do my best to cover at least the most important aspects of this subject. So these are the most important subtopics of this topic that I plan to cover in this talk. And I try to make it as non-technical as possible because I don't assume anyone being an expert in machine learning or even data science. Also, you can use these subtopics as starting points if you want to do your own research, because this is a very deep and intriguing subject. And if you may want to research it further, there's plenty of material out there, so you can use these as good starting points. So let's start with some definitions about machine learning and about its value in data science, especially nowadays. First of all, what are data analytics? Data analytics is a discipline of analyzing data to understand it, to communicate its essence, and potentially make predictions about it. This last part is very important because through it, we have a new field altogether in the past few years called data science. So many people view it as a kind of data analytics, but more advanced, because in data science, we use more advanced models and we focus a lot on predictive analytics. We focus a lot about the future, about making predictions, because understanding the data is one thing, but being able to predict things based on this data, it's a whole different ball game. And it's not as easy as it may sound, because you can do predictions fairly easily, but if you want to do good predictions, accurate predictions, you have to use more advanced methods and methodologies. And one such methodology is machine learning, which is an analytics paradigm based on the data-driven approach, as well as heuristics and scalable algorithms. We'll talk more about all these matters later on. And the importance of machine learning is really understood when we deal with modern problems, which are ridden with complexity and an abundance of data. And of course, having lots of data is great. And everybody wants to have more and more data, especially when it's diverse. But it's not easy to process this data and make anything useful out of it with the conventional analytics models. Because these were designed a long time ago, and they didn't really tackle every aspect of the data sets that we encounter today, which may be very varied, have lots and lots of variables, and sometimes it's not just one signal that you have in that data. You may have a bunch of different signals. And if you want to make good and accurate predictions, you need to be able to harness at least most of these signals. So let's shift gears a bit and look at the data science pipeline, which is basically the backbone of data science work. And I can talk a lot about this pipeline. I can even have a whole talk about it, but I'll just focus on the most important aspects when it comes to machine learning and where machine learning fits in the whole picture. The data science pipeline is also important to remember. It is not set in stone because it's often more like a rule of thumb that every data scientist adapts to each problem. However, it's very, very useful when it comes to managing data science projects and monitoring progress through them. So this part here, the data modeling part of data science, is where machine learning is more relevant. And that comes into play in two different ways. It comes into play using a bunch of different heuristics that helps us understand the data better and draw some interesting insights from it, and from data models. And data models in machine learning and data science in general have to do with learning from data. It's about understanding the data and being able to put it in some kind of programmatical, algorithmical model that can help us also make inferences from it. And one thing that you observe as you look at this data science pipeline diagram is that the data is gradually refined into more and more useful stuff. So from the raw data that we have in the beginning, we get into something more actionable, or something more useful, and something more akin to information rather than data. And these data models in the data learning phase are what make this possible. And that's why machine learning is so essential, because it really helps us make this leap from data into information, something we can use in decision making and something we can use often in products and services in the business. And this final stage, information distillation, as I call it, is also very important when it comes to machine learning, because it involves data products. Data products are basically the data models we have created when we put them into applications that are standalone. And more often than not, these are deployed in the cloud. And all of these models, because they have all this understanding on the back end as the data models we have developed, they encapsulate all the data we have seen already, and they can make something useful out of it. And because they are accessible via APIs often, everybody can use them. You don't have to have a data scientist around to use a data product. And that's how the scalability aspect comes into play, as we'll talk more about later on. And this insight, deliverance, and visualization block here on the left is also very important, because it's basically a summary of what we have done in this iteration of the process. And that's what we share with the stakeholders of the project. And oftentimes we create lots of interesting visuals that summarize the performance of the models, for example, and any other findings we have. And all of these are use on the back end some data-driven metric to measure this performance. And this is also kind of machine learning too. So we have a bunch of different models and applications, as I just mentioned, but how are they applied? And what are the most relevant ones that come from machine learning? First of all, the data science model is an algorithmic system for performing a certain transformation process to dig deeper into the data and make predictions about it. That's not always the case, but in the majority of cases, that's what we do, because predictions are key for data science. That's what really drives the most value out of the data. And machine learning models tend to be distribution agnostic. They're also able to handle data as is, and they can handle complex data pretty well. And these are also very important differentiators of machine learning from other kinds of data analytics paradigms, as we'll see later on. But it's important to remember the first part, especially distribution agnostic, because this is common in every machine learning model. The machine learning models out there right now are so many and so diverse, and they can do so many different tasks, but they all have this thing in common. And when we have these models as standalone systems, as software, or in the form of applications, they're usually deployed on the cloud, and they're accessible through APIs, as I mentioned briefly previously. And that's what also drives more value from them, because this way, they're not something that is in the domain of the data team. It's something that everybody can access, everybody can make use of. And if a company is agile enough and has this in its business plan, it may actually make money from these models directly. But even if they don't make money, they don't sell them as services, they can actually help understand the functionality, help the customers and the users of their platforms understand their platforms better. So there are a bunch of different ways to do that. And here I'll try to focus on the more general kind of models, because there are so many, and I could actually spend the whole talk just talking about the different models. But in a nutshell, we have the predictive models, we have the clustering models, and the dimensionality reduction models. And in the first category, we have decision trees, random forests, the support vector machines, k-nearest neighbor, and now more and more, we have the artificial neural networks. And all of these are very common for predictive analytics. However, predictive analytics, although it's a big part of the science work, is not the only part. And we have the clustering models like k-means, dbScan, and various other similar algorithms. And these clustering models help us find groups in data. Oftentimes, these groups have to do with the rows of a data set. For example, the different customers we have. And they make things much easier, because it's much simpler to understand our customer base if we look at 5 different categories, for example, of customers, instead of just looking at every single one of them. But we can also cluster the data in terms of the columns, the different dimensions we have, the different features in the terms of data science. And this is also very useful, because if we want to do something useful with those features, we may want to group them first to understand them better. And because it's very easy to understand the data set if it has a dozen features or so, but if it has hundreds or even thousands, which is quite common nowadays, it's much more challenging to do this. And that's why we have this dimensional reduction methodology as well. And a bunch of machine learning models, especially today, are into this category. And these are methods that are different than principal component analysis, which is also quite commonly used in data science today, because the machine learning models go beyond PCA. PCA usually looks at linear combinations of the different variables we have and creates new features based on these combinations. And that's a beautiful way of summarizing, in a way, the different variables into a smaller group of variables and performing dimensional reduction as a result. But there are other ways to do that, using nonlinear combinations, for example, with models like UMAP or TSNE. And of course, there is the feature selection approach, which instead of combining the different features, tries to select the best ones. And that's a simple idea in theory, but if you want to apply this and you have a bunch of different features and they're all related somehow to each other and to what you're trying to predict, it's not a very simple matter then. If you're attending this talk, I imagine that you have already some idea about artificial intelligence. And if you haven't researched this matter much, you may be like most people and conflate those two fields. So although it's hard to try to differentiate them, especially nowadays, I'll try to do my best and explore how they are different so that you can understand them better. First of all, machine learning is a set of methods, metrics, and models for analyzing data in a data-driven way. So far, so good. Machine learning models, though, may make use of AI, but don't always do that. Oftentimes today, we use a lot of AI in machine learning, and that's because it offers a lot of advantages and because it's something that sells also. When somebody hears, oh, this company uses AI in its models, you think highly of it because there is so much hype as well about these technologies. And, you know, there is nothing wrong with that, but it's not just that. And also, you can use AI in many different ways, different systems, different applications, such as optimizers for optimization problems, very difficult optimization problems, which have nothing to do with machine learning. So the two of them are in a way different, and the communities of people involved in them are not the same. There may be a lot of overlap, especially today, but it's not the same. And that's something that you can explore better in a Venn diagram, as we see in a moment, and also help us understand better where deep learning fits in. You may have heard this term, and it has also attracted a lot of attention in both communities because it's basically the best of both worlds in a way. So here, if we have this circle on the left denoting everything machine learning related, be it models or heuristics or what have you, and this circle on the right showing everything artificial intelligence related, then you can see there is an overlap. There is something in the middle that has both, and that's where deep learning lives. Because deep learning is basically machine learning models that are based on AI. And the vast majority of these involve a bunch of different layers of a particular kind of graph called an artificial neural network. So these deep learning systems are basically artificial neural networks that are very, very large. And of course, beyond this overlap, there is the other areas which are mutually exclusive. And in the first case, we have the conventional machine learning models. And in the other case, we have optimization algorithms and many other more domain-specific kind of systems. For example, when you are dealing with self-driving cars, you may have lots of AI systems there, like computer vision systems. And all of these are great. And sometimes they're used in tandem with machine learning systems, but they're not the same. Like somebody can do this kind of work in AI and never deal with machine learning stuff. Of course, it's important to remember that all of this stuff is very useful when it comes to problem solving in a data science context. So we don't look down on either one of these areas. We actually try to employ as much as possible. And that's why many data scientists today make use of AI in their CVs to brand themselves as people knowledgeable in both of these disciplines. Another similar misconception about machine learning has to do with statistics. And this is particularly the case when somebody is not so knowledgeable about either one of these two fields. And there is some relationship between those two things, just like with AI, but they're also very different. So let's look at how they differ, really. As we saw previously, machine learning is a set of methods, metrics, and models for analyzing data in a data-driven way. And that is basically saying that it's void of assumptions about the data. Because the data-driven paradigm is basically looking at data as it is. We don't think about how it should be or how it could be. We just look at data as it is. We don't make any assumptions about the variables, what distributions they follow, and how they're related, and all that. Statistics makes heavy use of distributions. And wherever you see something with a P, like a P value, for example, anything probability related, that's usually based on some distribution. And that's a beautiful way of looking at the data, because if you have some kind of archetypical templates that you can put the data in, then it makes it much easier to analyze it and draw inferences out from it. And that has been done so far, because these templates, these distributions have been analyzed to death over the past century or so. So we are pretty confident when it comes to these distributions. But the problem is that these distributions don't always come about. We all like to think about data as following the bell curve, which is similar to this distribution diagram, the histogram in this graphic in the middle. But that's not always the case. If you have certain kind of data that is somewhat normalized in a certain way, and we have applied certain processes on it, maybe it will look very much like it. But if you don't do anything to the data, it will most likely look at something else. And although there are a few models that combine both approaches, such as the naive Bayes classifier or regressor, most of these models out there are either one or the other. They're either machine learning related or statistical. Of course, over the years, many people have tried to unite these two paradigms, but none of them have succeeded in a meaningful way. There have been lots of interesting attempts, and many people, for example, like to view the outputs of a machine learning system in terms of probabilities, so they can try to tie it to some kind of statistical model. But in essence, this is more manufactured than anything else, because you can have the output of this machine learning model and your confidence about the result expressed as a number that just shows confidence, like a confidence score. It doesn't have to be probability. But because we are used as people to probabilities and think in terms of percentages often, then that's why many people try to make this connection. Also, contrary to what some people think about the whole matter, machine learning models outperform statistical ones in every methodology. So in the past, it used to be that we were about the same, and there were cases that machine learning was better, but statistics was better in something else. But nowadays, when it comes to raw performance, statistical models can't cut it. And they may be useful in other ways, don't get me wrong. Statistics is still very useful in data science. But if you really care about performance and getting accuracy rate numbers really high, machine learning is usually the way to go. And finally, people who view machine learning and statistics as the same thing usually don't understand these paradigms well enough. Many of them come from a statistics background, so they see everything in terms of statistics, and some more modern practitioners view everything from a machine learning background because that's what they know better. And it's like this old adage that if you know how to use a hammer and nothing else, everything starts looking like a nail. The same thing applies here too. So let's shift gears a bit and think about the whole analytics paradigm beyond machine learning and the whole mindset that revolves around this way of looking at the data. Because machine learning is not just a methodology. I think it would be like an understatement to call it methodology. It's more like an analytics paradigm. It's a way of dealing with the data and a way of thinking about what we can do with the data. And if you have seen any of my work, you'll see the value I place in this mindset matter, because everything in data science is first and foremost a way of thinking, a way of perceiving what is there and thinking what we can do about it. And that's fine, because every discipline has its own mindset. But oftentimes nowadays, especially, people focus a lot on the techniques, on the technologies involved in data science, and they are very fascinating. But it's just tools, if you think about it. The ideas, the ways of processing the data, the potential products we can create, these are all about the mindset of data science. And machine learning encapsulates this mindset and has a bit of its own kind of mindset attached to it. And all this has to do with dealing with data as is and not forcing any mathematical models onto it in order to model this data. So when we look at the data and see, okay, well, we have these data points and we can plot them here, and that's what they are, and we don't think about them in any predefined way. We don't try to put them into some kind of template to understand them. If we just look at the data as is and analyze it like that, then we're doing machine learning kind of analysis. And also the models of machine learning derive from the data through some optimization process. Because the data is so vast and so complex, it's really hard to try to do anything useful with it as it is. We have to try to optimize parameters often when we do this analysis, because the different machine learning models may have their own unique way of dealing with the data, but they all have a set of parameters which they often need to optimize in order to draw something useful out of the whole matter. And this optimization process is not always something visible. Oftentimes it's in the back end. But in the more complex, more advanced models, particularly in the deep learning category of models, this optimization process is pretty out there. You can actually view it when you try to train the models, because the different training algorithms basically involve a lot of optimization methods under the hood. And machine learning is also a mindset as an empirical evidence-driven approach to problem solving. And that is very closely related to the scientific method. So when we say data science is like a kind of science, but not domain specific, because it can be applied in many different domains and many different hands-on business-related scenarios, that's because we have this approach to dealing with problems. We look at the evidence, we make some hypotheses, test them, try them out, and draw inferences based on that. And that is heavily based on the machine learning mindset. Now, what about math, particularly advanced math and machine learning? Because there is a misconception that if you want to do machine learning, you have to really be good at math and really know your stuff really well. But that's not always the case. There are only a few models in machine learning that make use of advanced mathematics, particularly multivariate calculus. And if you have looked into the more modern models, particularly the deep learning ones, you see that this is the case. And many people try to tackle machine learning from that angle, and they just go to the latest and greatest models, and they often have difficulty because these models, if you want to understand them fully, you have to delve into a multivariate kind of space and apply lots of different derivatives there and all that stuff. But that's not always the case in machine learning, because you can have simpler, many simpler models than that can also add value. For example, when you're working with a decision tree or a bunch of these decision trees together, like a random forest setting or a boosted trees kind of model, then you don't have this advanced math. And these are the conventional machine learning models that I mentioned earlier. And they all make use of some clever heuristics rather than complex math. And heuristics are something that's a bit misunderstood in data science, because there are people who think that they're just shortcuts that are not really adding much value, and other people who think that this is the best thing since sliced bread. It depends on how well you know heuristics and what you really can do with heuristics. Because even a very simple metric that can help you understand the content of information in a particular variable, that's a kind of heuristic. And all of these heuristics are always there, but people don't always use the term heuristic to describe them. And if you have something like this in place in a machine learning model, this can really take a really good shortcut around the math and in a way encapsulate a lot of information, a lot of useful information in the model, much like you would encapsulate a lot of domain knowledge in a decision rule system. The same way heuristics apply specific understandings of the data in a very complex and in a very elegant mathematical formula or algorithm often. So because of these heuristics, we have this shortcut around the mathematics and help develop models that are much faster to use and also easier to scale. And beyond that, there's a lot of room of improvement in machine learning if math were to be applied to its methods, because machine learning is an evolving field and it's not really, it hasn't achieved its potential yet. And if you look at the research that has been done in this area still, you can see that there is lots of things to be discovered, particularly when it comes to geometry-related methods and heuristics. For example, the latest dimensionality reduction methods that I have investigated, not by writing papers, but by understanding those papers and trying to create educational content around them. These involve a lot of advanced math. So if you really want to do research and advance the state of the art of machine learning, you have to know advanced math. But oftentimes this advanced math is there without expecting people, the users of these models, to understand it fully. So even in the more advanced models, you can still use them and use them well and understand what they yield, the outputs they yield, without understanding exactly how they work. Of course, the better you understand the models inside, the more confident you are about using them, and the easier it will be for you to tweak them. So what about the limits of machine learning and what it can accomplish in data science? Because it's easy to go into the other extreme. Instead of thinking that, okay, machine learning is not as good as we think, go to the extreme of thinking that, oh, machine learning can do everything. It's a panacea. But that's not the case. That's not the case with anything in data science, actually. Because although machine learning can greatly help data science, it's not a silver bullet and still relies on the data at hand. Many data scientists tend to forget that. And because they are very aware of what a good machine learning model can do and the really high accuracies it can yield, for example, they get this idea that, okay, well, this is always the case. This is going to yield this performance in our case too, in this particular data set. But if the data set is not good or large enough, we have a problem. And this bad quality data always yields poor results, even with the most advanced machine learning models. Because it's like the fuel you put in a vehicle. If the fuel is not good quality, if it doesn't have a high octane count, it's not going to give you lots of mileage, and it may even mess up your engine. Fortunately, here you're not going to have this problem. I mean, you're not going to have to have a computer meltdown because of bad quality data, but you may waste a lot of resources, a lot of time as well, trying to train a model with data that doesn't have any useful signal inside it. And that has to do often with insufficiency in the data. Because if you don't have enough data, the predictions you yield with the machine learning model, even if it's state of the art, or if it's a very, very clever and advanced heuristic, these predictions may not be related to reality, because the insufficiency of the model makes it very limited, very narrow. It's like somebody studying about a particular exam with only looking at one chapter of a book. If you have the whole book, you have a better understanding of what this whole matter is about, and you can have a better chance of passing the exam. The exam in this case is the problem at hand, and solving it with a high enough performance, particularly accuracy. So if you have lots of different data, then you have better understanding, better generalization around this data in your model, and you can yield better results. But unless you have this data there, no matter how good the model is, you can't really do much with it. Another misconception that is often encountered nowadays has to do with classification and regression being the only methodologies that machine learning has to offer. And this is particularly the case when it comes to beginners in this field. But what are classification and regression? Basically, these are a twin of methodologies that have to do with predicting a particular variable, which we usually call a target variable, using some inputs. And these inputs are what we call the features. So once you have refined all the data and you have developed some useful set of variables that are all of the same scale usually, then we have these features, the feature set, and we use that to make predictions. Now, you can do lots of things on the feature set itself, but when you have something specific that you are trying to predict, then you have a classification or a regression problem. And it's classification when you have a discrete variable that you want to predict. For example, when you're looking at stock data and you want to see if a particular stock is going to rise or go down. That's one or the other, 1 or 0. So it's a classification problem. You can have more than 2 different possibilities, like you can have the potential of it being about the same. And that's also classification. But when you want to predict the specific value of that stock, which can be any number, then this is a regression problem. And of course, there are unsupervised learning methods that are under the machine learning umbrella, such as the clustering and dimensional reduction we mentioned earlier, which are also possible with machine learning. So people tend to forget that. And the funny thing is that unless you do some proper unsupervised learning, it's really hard to get a good understanding of the data. So it's good to do that first before you do classification or regression or whatever you need to do. And beyond that, there are other methodologies such as recommender systems and the natural language processing, which are also within the machine learning realm. Nowadays, because natural language processing involves a lot of AI work, this is often considered part of AI too. And this involves basically turning text into numbers and processing those numbers to create something useful out of the text. This can be a summary of the text. It could be some predictive text, like, okay, what is the next word that is about to come in this data stream? Or it could be some kind of analysis of the text in terms of sentiment. Is this like a positive sentiment or a negative sentiment in this text? I mean, the people who write this review, for example, do they really like the product or not? You can tell all that from just the words they use. And recommender systems, as you may have already experienced through sites like Amazon, are basically systems that help you get something that you already like in a particular site. Usually, this is in an e-commerce setting, although it can be in things like, okay, recommendation of different books and movies, like in Netflix. And this involves more complex analysis than the basic classification and regression that we often use. Also, we have heuristics that play a key role in machine learning, as I already mentioned, even if many data science professionals tend to ignore this fact. I can talk about heuristics all day, but I'd rather not right now because that can be a topic for another talk. Also, we have self-learning systems and their variants, which are also part of machine learning, particularly deep learning. Because if you have a system that can learn the basics through some minimal supervision from a human user, or even no supervision at all, then you have something else, something that is more advanced. And this is definitely nothing to do with classification or regression, even if the task at hand is related to that, because the self-learning system learns by itself in a way. It feeds its own feedback loop for learning, and it doesn't require the human supervision like a classifier or a regressor system. And of course, there's so much more yet to be discovered in analytics that is possible through machine learning. And that's something that is always good to have in mind, that whatever we know right now is not the end of the road. There is much more to be discovered, and something that we are always reminded with the newest and greatest systems that come into play. For example, recently there has been a development about a kind of improving the quality of an image using an advanced machine learning system that takes as input a very low resolution image and yields a very high resolution image. And this has been done for years, but now it has been done so well that it's almost indistinguishable from the real image, the original high definition image. What about transparency in black box models? This is a very hot topic nowadays, and it's good to at least mention it here, because there is this misconception that machine learning models are black boxes. Transparency in a nutshell is being able to explain why a certain result is yielded, and sometimes how this result comes about. And this may seem pretty straightforward because many models are like that, in statistics at least, but it's not so easy to do, especially when you have lots and lots of different variables at play. A black box model is a model that doesn't have any meaningful level of transparency. And many machine learning models that are used today, particularly deep learning models, are like that. They're black box models because whatever happens in them is a bit of a mystery. You know what goes in, you know what comes out, but how this output comes about, it's anyone's guess. And sometimes even the creators of these models don't know what's happening exactly. And of course, there are many machine learning models that offer some transparency, and people tend to forget that. Even if the most advanced machine learning models don't offer transparency, it doesn't mean that all of them are the same. It's more like a spectrum, if you think about it, where you have the super transparent models on one end and the black boxes on the other end. But there is lots of space in between. For example, a decision tree can tell you a lot about which variables come into play and when, and how the result comes about. A random forest or a boosted trees ensemble can tell you which variables in general are the most important and how much so. And there are many other models like that. And also more and more models nowadays have a confidence score attached to their outputs. And that in a way helps you understand what's happening and whether the prediction is reliable or not. What's more, we have this idea that machine learning models don't require much preparation. They're more like plug and play kind of objects. But that's not the case. Most machine learning models still require some preparation work, particularly for the features they use. So this feature engineering work we do in the beginning of the data science pipeline is oftentimes essential in many machine learning models. Of course, deep learning models are more of an exception because they need minimal preparation work to function. You may still need to do some things there, like if you have a categorical variable, you may need to break it into binary ones. But beyond that, you don't need to do anything else. However, in practice, you start with something simpler and then go into more advanced stuff. So this preparation work is usually done anyway. And of course, you can make use of other machine learning models for some of this preparation work. For example, you can use a particular dimensionality reduction model called autoencoder to do this dimensionality reduction first, and then put the results, these advanced features that it yields, into some conventional machine learning model. And this way you get the best of both worlds. You may get some interpretability from the conventional machine learning model, e.g. Decision tree, and you can also get the high performance that the autoencoder has. When it comes to education, this is another big misconception when it comes to educating someone in machine learning, because many people advertise courses for 2 or 3 months and they can teach you everything you need to know about machine learning, but this is not often very realistic. Even experienced STEM professionals need some time to get around the whole machine learning matter and get it down at a decent level. So just because somebody understands math and programming, it doesn't make them an expert in machine learning within a couple of months. I would say at least 6 months is essential, even if somebody is technical already. What's more, just like other parts of data science, machine learning is easy to learn, but quite hard to master. So if you really want to do something useful with machine learning and also differentiate yourself from other practitioners in this field, you have to really dig deep into this field and learn it inside out. And that takes often years to do. And of course, effective education related to machine learning today involves a great deal of hands-on work and one-on-one mentoring. The hands-on work is sometimes a given when you look into the machine learning curriculum of any course, because even if you learn the concepts inside out, you still have to be able to apply them, and that requires a lot of hands-on programming work, and that's not so easy to learn without doing it again and again over many different programs and many different data sets. And the mentoring is also kind of essential, because if you are a beginner in this area especially, you may get overwhelmed, or you may not understand things properly and still continue until the end of the course and not know things that well. The mentor can help you understand what you don't know, and also hold your hand in the other aspects of the whole learning. And even if you're a professional already in the field, it's not a bad idea to have a mentor, even if you don't meet them very often. To get you started with machine learning learning and data science learning as well, these are some resources that I would recommend. The book on the top left is the one I have published relatively recently, and it's all about machine learning using a very popular language called Julia, which is also high performance. The box at the bottom left, Thinkful, is an online educational platform that has a lot of technical courses, and a couple of them are data science related, and they involve a lot of mentoring as well on a weekly basis. And if you have been to the PebbleU platform, you may recognize some of this material. This is all the stuff I have developed over the past few years that Steve mentioned at the beginning, and most of them are videos, so they're pretty easy to follow and maybe even enjoyable. So if you haven't checked out PebbleU, check it out now. It's really worth your time. Also, we have the topic of frameworks and cloud and machine learning, and this has to do with scalability, which is a very important aspect of this field, because it's great to have a model that works, but if it doesn't scale very well, what's the point? You can't really apply it and make it available to many people. And that's why we use often these frameworks, which are standalone collection of methods and processes that are usually available on the cloud, and they help you put these machine learning models in production more efficiently and guide you through the whole training and testing phase. And they also provide lots of useful visuals in the process and make the whole process more streamlined. Typical such frameworks are TensorFlow, MXNet, and Keras, and all of these are written in a low-level language like C++. But fortunately, they interface with data scientists using Python, usually. More modern models, or rather frameworks, like MXNet, for example, use other languages as well, including Julia. And most cloud platforms support frameworks of machine learning nowadays, and they often come with some solutions pre-configured. So you don't have to install everything. They may have already the framework there. You just need to put your data and train the models you need to use and deploy them afterwards. So you don't have to be an expert in data engineering. If you are, that's great. If you have data engineering in the team, they would love this, but it's not always essential. Let's now wrap up with some useful considerations about machine learning and data science and related topics. First of all, machine learning is always evolving, as I mentioned previously, but data scientists can't always keep up. So it's very important to have this continuous education mentality and always try to learn new things. Never assume that we know everything, because the field has always surprises for us. And usually there are good surprises, because there's always some newer and better model out there which we may be able to use. Of course, the amount of data is a big matter in machine learning, and I have stressed it already, but it's not always the case that we need tons of data to do something useful. We may be able to have a conventional machine learning model with a limited amount of data, and it may still yield value. And as we gather more and more data, then we can have more sophisticated models in place as well. But we can still have a proof of concept, for example, using the data that we have in our organization, even if it's not vast. Also, no amount of machine learning know-how can offset the lack of ethics in data science. It's always good to remember that we're dealing with people often behind the data. It's not just ones and zeros. And whenever we deal with personally identifiable information specifically, we have to take into account that people's privacy may be at stake. So we have to make an extra effort to keep that privacy in check and make sure that it cannot be compromised. And finally, if you wish to make the most of machine learning, it's best to go beyond the methods that are provided in the relevant packages. Nowadays, in languages like Python and Julia and other high-level languages, there's a package for everything. So you don't really have to code much from scratch. But if you really want to go in depth in machine learning, it is advisable to go beyond these packages and try to code something from scratch once in a while to understand the algorithms better, and perhaps even make tweaks on the existing methods to make them more suitable to the product at hand that you're trying to develop. And of course, if you are more on the creative side, you can come up with your own methods, machine learning methods that you can implement to make the whole project easier. So that's all I had for you for today. Thank you very much for your attention. And as I mentioned in the beginning, if you want to download the slides deck, you can use this QR code on the right. If you have any questions, please go ahead. Thanks.
Thank you, Zach. That was wonderful. A couple questions. So how do you explain? So sometimes people ask me, okay, what is data modeling and what is data modeling? In other words, like, how does data modeling differ from a structural perspective from how data modeling might be in a data science machine learning perspective? And I remember a couple years ago in Data Modeling Zone, you had a really good distinction between the two. Can you summarize that? Like, how someone comes up to you and says, how does data modeling from a machine learning perspective differ from a database perspective? How would you answer that?
That's a very good question, and I often ask myself that, because when it comes to explaining this to someone who knows data modeling from a database perspective, it may seem like the two things are clashing. And to some extent they are, because we use the same term for somewhat different things. Data modeling, the way I understand it in your field, has to do with modeling the information and the other business-related processes in a way that can help the business and also drive value from the data, the low-level data that is available in those databases. Also designing those databases in an efficient way. But in data science, the data model is something very specific that has to do with analyzing the data. So a data model doesn't tell you how you should organize the data. It assumes that the data is already organized. You have given it already the data in the form of features and oftentimes a target variable. And the data model tries to make this mapping, this connection between the two. And this is not a very simple task, especially when you have lots of data in. But to do it in an efficient way, tries to do. I lost the feed for a second, sorry.
I was with you.
I hope this answers the question.
Way. Yep. Okay. Thank you, Zach. So I was with you all the way to the end. You said kind of do it in an efficient way, and I lost you right there.
Right. Sorry about the glitches of live streaming.
Yes, I know. Exactly.
Well, it's about making this connection, this mapping, and doing it so in a scalable and efficient way that can be used with new data as well. So I hope this answers it.
Yeah, that's a great distinction. Thank you. Thank you, Zach. Does anybody else have questions for Zach as well? We have just another minute or two. Zach, do you think from a career perspective that it's better for somebody to have expertise in a certain business industry like manufacturing or banking and then add to that data science, machine learning? Or do you think it's better to be more of a generalist and kind of know data science, machine learning, and be able to work in different industries?
That's another good question. I would say the latter, because if you are more familiar with what data science can do and you have experience with all kinds of data, then you can apply these methods in different domains. But if you have only domain knowledge in manufacturing or marketing, and that particular area, you may be able to do add a lot of value in that area, but maybe it won't be so easy to add value somewhere else. So you limit basically your job prospects. Of course, you can still learn about data science more and be able to become more flexible, more versatile. But this takes time as well.
Okay, great. Thank you, Zach. Thank you very much for
Yeah,
that
no
great
problem.
presentation.
All right. Thank you very much, Zach, for this presentation. Before we break for lunch, there's a few messages that I wanted to share with you. First of all, Steve will actually run a keynote presentation just after lunch around 1:30 later today. So definitely not to be missed, talking about the power of business terms and the business terms model. So hopefully many of you will join us for that. And then also reminding you of the rest of the agenda. So we have at 2:30 the Meet the Partners networking opportunity. So don't hesitate to go and meet the exhibitors, the partners, the sponsors of this conference. There's also a zone where you can meet the partners in their virtual booths. So that's definitely something that's worth to check out. And then regular sessions will start again at 3 p.m. So there you will have again a choice between two parallel tracks and many more great speakers to come. So thanks again for your attention. Thanks, Zach, for a very interesting presentation, and see you soon in one of the other sessions. Bye for now.
Thanks. Take care.